So the phases were discussed earlier in this electrical and electronic circuits course in this particular lecture. Uh, you can probably check this out and refresh your discussion, your remembrance of this discussion. So basically what we have here is nothing but a complex number, okay, a complex number with a magnitude and a phase component. So if we have e power j omega t, then this is the complex component. Basically the magnitude of this component is always 1. So if we try and compute the magnitude, this is always 1, okay, because we can write this as cos omega t plus j sin omega t, and you compute the magnitude. Basically this is e power j omega t. The horizontal component is cos omega t and the vertical component is the imaginary component, which is sin omega t. Okay. So as you can see here, we can decompose that into real and imaginary parts, the cos and the sine, and the length of this line can be given by this Pythagoras theorem. Length of this line is sin omega t, the length of this line is cos omega t. Obviously the length of the hypotenuse is square root of cos square plus sine square, which is essentially 1 all the time. So this is 1, okay. So this magnitude is always 1. So what is this angle? The angle is nothing but tan inverse of the opposite side by the adjacent side, which is basically nothing but sin omega t by cos omega t, okay, which is tan inverse of the real part coming in the denominator and the imaginary part coming in the numerator. Okay. This is how we represent a phasor. Now the phasor need not always have magnitude 1, it can have a different magnitude, it can have some other magnitude r, okay. In other words, we can just have this line to be just scaled by r, which means the corresponding x-axis, y-axis values, the real and imaginary, they also get scaled with that r, okay. That's it. So we can very compactly represent everything as some e power some sigma plus j omega t. What is this? This is nothing but e power sigma times e power j omega t, and this is, we'll call this as r. Any given number you can represent that as e power sigma, any given positive number, okay, because this magnitude is always positive. So we can always represent that as e power some sigma. Sigma can be positive or negative. If sigma is negative, then r is less than 1. If sigma is positive, then it can be greater, r, the magnitude is greater than 1. So any complex phasor can be represented using this representation, where the magnitude is given by this component and the phase is given by this component, okay. So in this case, the phase is a function of time, that is, as time changes, the phase also changes proportionately. This is what leads to frequency, right? So what is, if you remember what is frequency? Frequency is the rate of change of phase. So if I say that this is phase, then the frequency is d phi by dt. In this case, the angular frequency, which is omega radians per second, right? So that's what we get here. So it's not necessary that we should always have a time varying phase. We can also have something of this form, okay, which means here the phase is now varying with time, plus there is a fixed phase component. So out of phase signals or in phase signals will have a different phi. In phase means phi should be equal between two different signals. Out of phase signals will have different components here, okay. Now that we have understood how you can represent a phasor with just a complex number, let us see how it is actually useful in a circuit when we analyze a circuit. A simple circuit is what we are going to consider, right? We'll take a resistor and a capacitor, a simple RC circuit. Okay. So here we'll apply some voltage source, and let's call this the voltage source, and the voltage across the resistor, and this is the voltage across the capacitor. Now if we want to find out what is the voltage across this capacitor and the resistor given some voltage here. Let's call this is the applied voltage. This is V. This is V of t. Okay. We are applying an AC voltage which keeps going up and down with frequency given by omega, and its magnitude is V naught. Okay. So if V naught is, let's say, 10, then the frequency is, let's say, 50 hertz, then the voltage oscillates between 10 volts and minus 10 volts with a frequency of 50 hertz. Okay. Then within a second it alternates 50 times. Now if we want to find out the corresponding voltage here and across the capacitor, how do we do that? We know this traditional equation, right? So V is equal to IR, we are going to just use that. So VR is equal to I times the resistance, that's all we have. So the first equation is basically nothing but KVL, right? Kirchhoff's voltage law. In this entire circuit, this has to be equal. So that's what we have done here. And we are just going to use Ohm's law for each of these voltage values. This is the voltage across the resistance, and this is the voltage across the capacitance, which you can write it as an integral. And this is the total voltage in the current. From this, if I have to compute VR and VC, we have to solve for this equation and then get the I of t. So one way to get this I of t is, now you can differentiate on both sides. You would get R di by dt to be equal to plus I times C to be equal to V naught d by dt cos omega t. So this is a known value. This is V naught sin omega t, and this is some I by C, and this is the C is known constant, R is a known constant. So basically we have a differential equation of the form, let's say, dx by dt plus some Vx is equal to some C of t. This is what we have. We have to solve for this differential equation. So that's, it will take quite some time, like 20-30 minutes. You use your solutions of ODE, ordinary differential equations, plug in all those techniques here, solve it. If you solve it, then you can find out what is I of t, and you plug in I of t in this expression, you will get VR of t. Okay? And then plug in I of t here, integrate it, you will get this expression. So solving this ordinary differential equation gives us these two solutions, okay, where there is a phase difference between the voltage across the resistance and the voltage that was actually applied. The voltage that was actually applied was V naught cos omega t, whereas what we are seeing across the resistance is a reduced magnitude. That's okay. That's expected. There is a resistance, so voltage will drop. But what is more important is there is a phase difference, and the phase difference is given by this value. Similarly, there is a phase difference along this capacitor also. Because there is an introduction of this capacitance, there is a phase difference that is observed between the input and the output. This is what that was quite important, and this is what we wanted to model. And we are able to see that even without any complex number. But the problem is we had to go through solution of this differential equation, which is quite involved, which is quite hard. Whereas if we had used a complex phasor or a complex sinusoid, things would have been easier. So we'll start out with the same equation, okay, exactly what we did earlier. And then what we are going to now say is, now the applied voltage is a phasor. You have the magnitude, you have the phase, and let's say the current is also what we are going to claim as a phasor with some magnitude A and some phase. Okay, of course the input frequency is omega, so we are expecting the current should also have the same frequency. So there is a frequency, but of course there could be a phase difference, which means this A will now incorporate the phase difference also. Now how to find this A? Now let's plug in this phasor value here in this expression. Okay, we plug in the phasor value in this expression. What do we get here? A e power j omega naught t times R plus 1 by C. Now integrate this phasor. If you integrate this phasor, what do you get? 1 by j omega times e power j omega. This is a very nice property of a phasor. So if you integrate a phasor, you get the same phasor as such back with some scaled value. If you differentiate it, you would have gotten something like this, same thing. So this is a very nice property of phasors. So they are what are called as eigenfunctions of, this is a terminology, forget it if it sounds too fancy, but what it simply means is that you have an integral block or a derivative block, you pass a phasor through it, okay, it can be whatever magnitude, what you get at the output is exactly the same phasor with a scaling factor, and that scaling factor depends upon the frequency. Okay. For an integrator, it is 1 by j omega. For a differentiator, it's just j omega. So you get exactly the same phasor at the output of the integral and the derivative block. Only thing is they are scaled with some complex numbers. Okay, and this complex number is what that will introduce a phase shift. What is this complex number? I can write this j here as e power some j pi by 2. Right. Similarly, this j here I can write it as e power minus j pi by 2. Right. So this entire phasor now can be written as e power j omega t times e power j minus pi by 2 times 1 by omega. In other words, the amplitude is reduced by some amount and there is a phase shift. All this could be written as some phasor of this form. So there is a phase shift of minus pi by 2 due to this integrator and plus pi by 2 due to this differentiator. So plugging this back here, what do we see? When there is a capacitance, we see that there is a phase shift by minus pi by 2. Again, this corresponds directly to the voltage lag that we saw earlier. Voltage is lagging, right? That's what is happening. We are seeing the voltage lag by minus pi by 2 here when we plug in. Okay, this is equal to V naught e power j omega t. Okay, great. Now in this equation, just subtract or divide both sides by e power j omega t. So once you divide both sides by e power j omega t, you get AR plus 1 by C j omega to be equal to V naught. Okay, sorry, there is an A here and there is an A here, right? So this gives that A equals V naught divided by R plus 1 by j c omega, which gives us this value. Okay, so this is quite simple compared to solving a differential equation, right? So all you had to do here was just plug in that I is equal to e power j omega t, and then there is an integral. But then the nice part of having the phasor is that feed in a phasor to this integral operation, outcome is yet again a phasor, the same phasor, only that there is a scaling factor. Similarly, if there was a derivative, feed in a phasor, output is also same phasor, just a multiplication factor. So we don't have the problem of solving a huge differential equation and then trying to get the solution. Just whatever is the input, write it as such, multiplied with some 1 by j omega or j omega, and then from that we can find out what should be the magnitude. Okay, and then we found out the magnitude here. So the magnitude is containing a complex number, of course. So which means we have to find out what is the phase that comes out of it. There will be a phase shift. So given that now I of t is of this form, how do we find out the voltage across the resistance? Simply multiply A e power j omega t with R and we are done. We will get this expression. Okay, we just multiply this A with e power j omega t that we have here and times R. What we have here is this expression. So now you compute the magnitude of this expression. Now what is the phase of this entire complex number? The phase of this complex number is once again given by, so you can just compute this as 1 by, basically divide both the numerator and denominator by jrc omega. So this is what we have, right? So this is as good as, let's simplify this even further. Okay, so what is the phase here? So tan inverse of b by a. So what is the tan inverse b by a? So this is b. What is b? Is the imaginary part. This is the imaginary part. The real part is just 1. So this is the phase for the denominator. For this entire complex number, all you have to do is just multiply with a -1, because this is 1 by e power j theta. So this is equal to e power minus j theta, right? So all you have to do is just get the phase by multiplying with a -1, okay, which gives us nothing but tan inverse of 1 by rc omega, which exactly was what we had here, right? So we get exactly the same expression as before. So you look at this. So we got V naught some magnitude times cos omega t plus phi, and that is what we are getting here. The same magnitude as what we had here, and it clearly says that the phase is now different by phi. So we see that the voltage across the resistor is out of phase by phi. Do the same thing for the capacitor. How do you compute the voltage across the capacitor? You just take this expression, or you can take this expression directly. Okay, plug in a here. Okay, you plug in a here, we get this expression. Okay, so as before, magnitude directly follows from this. How do you compute the phase? You compute the phase by computing this angle and then subtracting it or multiplying that with -1. So if you multiply that with -1, you get a different value, but only thing that you have to note is you have to use this identity. This identity tells that tan inverse of theta plus tan inverse of 1 by theta. Basically, in this case, tan inverse of rc omega plus tan inverse of 1 by rc omega is equal to pi by 2. We'll be getting tan inverse of rc omega, right? And that is in fact equal to nothing but phi. There is a phi, this is phi, this component is phi, equal to pi by 2. So we'll have tan inverse of rc omega here, which is equal to pi by 2 minus phi, and this is the denominator. To compute the phase of the entire complex number, which is reciprocal of this, you have to take the negative sign of that, which means this is the phase. So it says that now the voltage across the capacitor is out of phase with the voltage at the input by pi minus pi by 2. So this pi by minus pi by 2 results in the cos turning into a sine, and there is this additional out of phase component that we are getting here. So all we did here was just use a phasor representation, and then we did not even see how to solve this ordinary differential equation. Right? If we had solved this, it would have taken another half an hour. But then in just 10 minutes, we were able to solve this voltage across the resistance and voltage across this capacitance and find out what would be the phase difference and whatever is the magnitude, right? It was as simple as that. All we had to keep in mind was that the phasor, when fed as the input to an integrator, the output is the phasor multiplied with 1 by j omega. Phasor, when given as the input to a derivative function, is just the phasor multiplied with j omega. That is it. So the two important things that we had to keep in mind here is so if we just keep this in mind, then we are easily able to solve this set of differential equations or integral equations and then find out what would be the voltage across the resistance, voltage across the capacitance in a very simple form, and directly compute what would be the phase difference and all. So imagine if this is the case for a simple RC circuit. Now, a filter that you design in practice might have several resistors, several capacitors, several inductors, and to analyze that using differential equations and solving these ODEs would become a nightmare. Okay, to make that easy, we are using phasors. So this phasor representation helps us to simplify our analysis.